carbon cycle. Okay, so this is the point in the class when we crowdsource a lot of information, because many of you know a whole lot more biology than me. Welcome to it. Let's say we know different things. To me, the hardest part of this is the vocabulary. Margaret has to rely on what she did online in biology honors with, like, Wesley Adams, perhaps. Myers? Okay.
Oh, you missed Myers and not Myers. No, for freshman year, so like only the last. But yes.
And so, to me, the vocabulary gets a little bit hairy at some points, and like, there's a totally unfair question on that homework I just gave you. Ooh, good luck. But we'll talk about it because I know it's there because I did the homework after last class, so it'll all be good. Does anyone make tea this way?
How?
Yeah.
What is that? Oh, I just hold it back in there. Like without. It depends on if you make the tea.
So if you make tea without a tea bag, are you always making it in a pot for communal consumption, or do you make it for yourself?
For myself.
I found my people, okay. Like Carl looked at this and he's like, that's not how we do tea. We all come together. And I was like,
Tea time.
you can invite me anytime, Carl. This is how I make tea for myself. I don't know, I didn't expect to be paid for my personal tea. There it was. He's not invited me yet, in case you're keeping track. It's been a week. Okay, the black stuff is the SL, the red stuff is the HL. You might be surprised that nucleic acids are only HL. It's a relatively easy topic that just relies on some background knowledge really about DNA and RNA. But we do learn how to draw the structures. So we'll talk about drawing base pairs, which are in the data booklet, but we're gonna organize them such that we can show the hydrogen bonding. So I think you guys know that there's like a zipper, for lack of a better word, in the center of DNA that is made out of hydrogen bonds between those nitrogenous bases. But what we're gonna practice doing is looking at the chemical structure and like putting the actual hydrogen bonds in. Understanding why some relationships are stronger than others, and that must have something to do with the Tata box. Thank you. That's what you call it, isn't it?
There is a Tata box. Like, I remember.
Yes. There's a Tata box.
There is a Tata box.
I feel like now I'm talking about movies. Like, I mean, it got worse and worse. The first time I said it, I was like confident. And now it's like, I'm not talking about anything wrong. Like, don't T and A have just 2 hydrogen bonds while G and C have 3?
Yes.
And so there are some implications of that difference in the number of hydrogen bonds between the nitrogenous bases and why you might make that section of your DNA out of T's and A's instead of G's and C's. My understanding of biology is like profoundly different than yours. When I think about proteins, I think about amino acids. And like I think about the structure of the R group, not just that there's an R group. When I think about an alpha helix and a beta sheet, I want to know why do the residues want to be on the inside of the helix or on the outside of the sheet? What do those residues have in common with regard to how they're going to interact with an aqueous environment? Like what are we hiding or what are we showing? This stuff is not super duper hard. It's just, I think, not the way that alpha and beta are presented to you in biology. So I'm again going to say that it relies a lot on the vocabulary that you probably learned in bio honors if you're like not in biology now. But if you are in biology, that vocabulary is just free. Like you're not confused about what I mean by an alpha helix. You're not going to be surprised when we figure out how many turns it takes to get that hydrogen bond between the peptides. Okay, so we're going to break things down into the shapes, sort of, or classes of different molecules. We'll start with proteins, lipids, carbs, vitamins, and then we'll do this poop B.S. unit, biochemistry and the environment. When they rewrote the curriculum for you guys, they decided that every option needs to have an environmental component. And so we're gonna talk about xenobiotics and detergents. It's just like a litany of things that we need to have like a few flashcards about to kind of keep track of. It's disjointed is what makes it hard, not that there's not interesting stuff to learn. In the HL part, proteins come up again, and we'll talk about their kinetics. I haven't decided if I'm gonna move this up here, to be honest, just to make it a little more fluid. We'll figure that out next week. DNA's pigments, so that's gonna be mostly hemoglobin and photosynthesis chlorophyll. I hear you guys are talking about pregnancy in biology right now. I think at some point you might talk about fetal hemoglobin, but it's clear we haven't talked about it. It's different than adult hemoglobin and why it might be different and how that impacts the transfer of oxygen across the placenta. So sometimes we pretend to be like realistic biologists, like caring about things that are interesting. We'll talk about like vitamin A in this context. We could talk about some photosystems. And then everyone's favorite is going back and talking about the stereochemistry of biomolecules. So Margaret knows that we have dextrose and levulose. You might know that penicillin attacks D-alanine on the surface of the capsid of whatever bugaboo is inside you making you sick. You don't have that amino acid, so it does not attack you. You have L-alanine, or I have my D and my L backwards, and you guys can ridicule me after mocks when I get this right. But like penicillin has a target that is a particular chirality of alanine that is not the one that you express. How convenient. Stereochemistry and biomolecules. I am terrible at doing slides. At some point we get to some things I can't draw. That doesn't really happen today, but I have, a few different sets of slides for this chapter, so I thought I'd see how it felt. I did this yesterday, so the experiment, it's been done, and now you just suffer the consequences. These are the things we have to do. Shapes and structures of biomolecules define their function. I think that whole idea is central to biology. Some of you might know that my very favorite protein is ATP synthase. ATP synthase is a protein with quaternary structure. Does anyone remember what quaternary structure is? A whole bunch of proteins come together to make one superstructure. It's either 26 or 29 folded proteins come together to make each and every ATP synthase, which when I draw it on the board looks just like a penis. Found that out teaching a 9th grade biology class. Then you have the H+ ions flowing through. You're like, I just want to end everything. Everything. But like, is it not magical? How many ATP synthases do you think you have in a cell? I mean, I think you have a lot, and every one of those is a self-assembly of already folded proteins. Like, how does your body, it's not your body doing it, know how to fold those proteins? How do the proteins self-assemble themselves? How do we do protein folding? And how do those proteins then come together to make a structure that actually serves like a little machine? Like a little pump of protons. Like, how do we take the shapes of molecules and turn them into a living organism? That is this unit. That is crazy. And can you believe you're made of molecules? Do you ever think that thought? Like, is it not absolutely mind-blowing that it's the shape of molecules and their interactions that is making you work right now? Mind-blowing. Okay, so I'm going to have an essential question on that board before you come back to next class, because I'm being bullied, and we'll say something to the effect of how excited I am about this thing. Because to me, that's the overarching wonder of biochemistry. We are going to focus on humans. So if Amarachi got some information about prokaryotic cells and how they do some business, like, it's good, but we're not going there, right? Like, she learns the stuff in patho, it's interesting, we can share it, but we have like one system in mind, that system. So it's limited. Okay, here we go. Metabolic processes take place in aqueous solutions in a narrow range of pH and temperature. Did you know that we believe that life started because some molecules organized to make a membrane? And that membrane meant there was an inside and an outside. And chemistry did happen in that inside. That inside is protected. You guys are going to use fancy words like homeostasis. But I'm going to use simple words like the inside was special. It was protected from the outside. Not a biologist. We're going to come up with definitions of anabolism and catabolism. We're going to talk about how condensation and hydrolysis are the two big reactions of making biopolymers. We're going to pretend we know something about photosynthesis and cellular respiration. And let me tell you, we don't know much at all. So anyone who's thinking that they're going to draw me a citric acid cycle, disavow yourself of that notion, go show off to Myers and Holmes. We are not going to do that here. The two skills you have to have are like identifying if something's condensation or hydrolysis, check, and balancing the carbon and the oxygen in the atmosphere by looking at the complementarity, made that word up right now, of photosynthesis and respiration. Fun fact, respiration has nothing to do with breathing. It's crazy, isn't it?
Yeah.
I get more joy out of this than you do. It's totally crazy. I mean, what does respirate mean? It means to breathe.
Yeah, I thought cellular respiration was like before the very beginning of IV bio, I thought it was like cells.
Breathing. Thank you for saying it out loud. So until I taught biology, I don't know that I appreciated that plants do cellular respiration.
I didn't either. That was shocking.
Like, I mean, it was always this like plants, animals, and it was like, oh, that don't make no sense, does it? And it was like light bulb moment. What's metabolism? Andrea Lee's answer was, what makes me fat? Or the lack of which that makes me fat. Like, that's just harsh. Okay, so you guys seem to know what metabolism is. Good for you. Anabolism? Your simple-minded teacher who doesn't know this remembers that Arnold Schwarzenegger was a big, built-up man. He grew lots of muscles. He took lots of anabolic steroids. Arnold and anabolic both start with the letter A. If I had to guess what analysis meant, to tell you the truth, I would think it is breaking down a math problem. If I had to tell you what anatomy meant, I would think it is breaking something down into slices. Tomi means to cut or to slice. So this word is not like a cognate for me. Again, you guys know it because you've learned it somewhere else, but Margaret and I are trying to make some sense of this. So if I'm trying to use some Latin words, it doesn't really go for me. So Arnold and anabolic, it is the building up of biomolecules. Or maybe precursors. And it typically is going to take energy. When you say catalyst, what does that mean to you? The effort. Okay. That activation energy. Yeah. Like I find these words. So what is catabolism?
Breaking down bigger
Yes. Does breaking bonds cost energy or release energy? does. This is very counterintuitive to a lot of us. You might think that ATP breaking a bond to become ADP in a phosphate would be like a nice way to release energy if you were a biologist. But if you're a chemist, you would assume perhaps that took some energy because you're breaking the phosphate bond off. It is counterintuitive. It is true. It's because of that aqueous environment that things get weird. The bond energies that we look at in the gas phase are not adequate. It's because of a lot of different reactions that are going on. There's a big entropy term involved. So it is just like non-obvious. A metabolic pathway is a transformation of reactants into products. Each intermediate is a metabolite. The Hotter book has a picture of like what goes on in a cell, and there are thousands of metabolites, all connected in different ways. Just what we call the intermediates. So, like if you were to take glucose and start cellular respiration, I feel like the first step is you snip glucose into two pieces. What is that? What's the name of the product? Pyruvic acid. Thank you, pyruvate. That would be a metabolite, intermediate in the step. You think then that the pyruvate goes on and moves from the cytoplasm into somewhere and does some more fantasticness? I don't care. Each one of those steps is a glorious piece of my metabolic pathway. Each one of the products that you make and then use again, it's called a metabolite. We recycle a lot of stuff in cells and in the ecosystem. Nutrient cycle, carbon cycle. What's important perhaps to know is that the process of making something is different than the process of unmaking it. The enzymes that are used to facilitate one process will be different than the enzymes that are used to facilitate the opposite process. And because of that, you don't have like some weird loop that does nothing. They don't exactly sum to zero. A point that doesn't impact any answers to questions, but if you're thinking back to like Hess's law, and like, why do you gotta keep eating if everything's so cyclic? It's because there are actually different processes going on, even though the reactants and the products might appear to be the same. Slides. There's so many different reasons I hate this. Biochemistry studies the chemical processes in living cells. Biochemical processes, collectively known as your metabolism, are complex and involve many chemical reactions happening at the same place at the same time. Some are anabolic and some are catabolic. Give an example of each. Love it. So we could take a polypeptide and break it down as an example of catastrophe. Thank you for that. We could take a polypeptide. So let's think about what a polypeptide has to look like. I'm going to draw a dipeptide because I have limited time and space. And so in this class, when we draw it, we follow the biologist convention of putting the N group on the left. Because, I think that's important to y'all. And this is going to be a dipeptide because I have made a single peptide linkage between two individual amino acids. So that looks like a dipeptide, I hope. In this class, we're going to be interested in these residues. There are 20 of them that occur in you. And so I have some favorites. Pretty fond of alanine. It makes one of the residues just methyl, like that one. Pretty fond of glycine. Makes one of those just hydrogen. Very easy to draw, guys. You do not need to be able to like throw down tryptophan if someone says like, yo, Elizabeth, draw me tryptophan. It's in the data booklet. The whole list of 20 amino acids is there. But we are gonna think about how we could classify them into different groups due to the interactions between residues, which Quinn will tell me has something to do with tertiary structure. Well, I know you will. So Amarachi told me that I could break this apart. The way I break this apart is by using hydrolysis. So I'm gonna add water to lyse this molecule. And this molecule is going to turn into the 2 amino acids. Again, alanine and glycine. Are these molecules that you've seen before, do you identify, functional groups that are familiar and friendly to you? That's good. You should see a carboxylic acid, you should see an amine. So could we actually name this molecule? It is an amino acid, but he has a name. What's the longest carbon chain? Ethane. I'm going to tell you that the oic is more important. So I'm going to tell you this is ethanoic acid. What's on my ethanoic acid? An amine. Is it at position 1 or position 2? And so we would refer to this as 2-amino ethanoic acid. Mr. Holmes might call it glycine. Ms. Myers might call it gly. There's also a 1-letter symbol for these because proteins are big. I don't happen to know what glycines is. I'll take anyone knowing it. It's not going to be G because there's glutamic acid. Sorry. We will not learn the 1-letter codes. I don't think they will ever come up, but we will use these 3-letter codes occasionally to point out the variability in structure. How about this guy? How would you name him? So what's the longest carbon chain? 3, so it's propanoic acid. Where is the amino? And so we actually refer to this whole class of molecules as 2 amino acids. How's that? Does that make sense? That the propanoic, the amino will always be on position 2 because the only group that we're going to change is this residue at the top. So it will always be true that it is sort of 1 carbon away from the coup. Yes?
Quick question, is it saying that it takes water to break those 2 apart?
Yes, ma'am. This is a hydrolysis reaction. It takes water to do it. The OH is going to go right there on the Q, and the H is going to go right there on the amine. That's going to allow me to do this. You guys taught me that the breaking down of things is supposed to release energy. Took me a minute, but I'm pretty sure. That's why we eat food, to break it down and release energy so I can give this amazing lesson. So my expectation is that delta G for this reaction is less than 0. That it is a spontaneous process, that energy is released. Now Aditi's going to tell me that she can certainly see that delta S is probably positive, which would support this being spontaneous because she's taking something complicated and turning it into something simple. That's appealing to me. We could try to see the sign of delta H based on the values in our data booklet, trying to use the bond enthalpies, but Emma's going to point out one more time that that's going to refer to things in the gas state, and this is going on in sort of the privacy of a cell, where many, many things are controlled. It is very different than that gas phase environment that we like to pretend to know about. The opposite of that catastrophe is Arnold coming together. And Arnold is into carbohydrates. Oh my God. Arnold's not into dry hexagons today. He's into carbohydrates. So if Margaret is unable to throw down the structure of glucose, where do you think she might find it? It is in fact in the data booklet.
Does it matter if the H or OH go on the top or the bottom? Because I feel like I could.
100%.
It does.
glucose, the third one is different?
Yeah. Yeah.
Like that's what makes this glucose.
Okay.
If you flip a different one, you have a different sugar.
The third one is.
The third one, so this is carbon number 1.
Oh, okay. The second one. That's
No, OH should be at the bottom. The third one is backwards. That's how I know it's glucose. And again, I suck at this. You guys are gonna remind me that carbon number 1 actually has a choice because there's a straight chain form of glucose. And so glucose is hanging out like my hands as a straight chain, a hexose sugar, and it can fold like this, or it can fold like this. And we refer to these two different decisions as alpha and beta. The difference that you would see in my drawing, this is known as a Hayworth projection. There's no Y in that Hayworth projection. We'll talk about it when we get to cars. It's gonna be right here. The data booklet will show you alpha glucose. You're expected to know that we will flop this to make beta glucose. So this is the one that goes up and down. This is gonna be the difference between amylose and cellulose. But these don't move.
Yeah. Just
Okay. So yes, we'll do that too. And we're gonna bond this with another unit of glucose. What do I call this disaccharide? Maltose. I'm making what Mohab would tell you is a 1,4 linkage between these two things. The notion of calling it a 1,4 linkage is one more time to count those carbons. When we count the carbons, we start with this one right here as number 1. This is number 4. I'm calling it a hexose sugar because there are 6 carbons in it. So hex meaning 6 and os meaning sugar. And what I'm going to do is I'm going to try to make a bond between the stuff on carbon 1 and the stuff on carbon 4. So we'll call that an alpha 1,4 linkage. That's what made this maltose, as Mohab suggested. The way we're going to make that bond is the OH and the OH are going to come together, and what do you think they're going to lose? So this is going to be a condensation reaction, and it's going to produce maltose, which I'm feeling kind of too lazy to draw. But if you want to give me a minute, I'll get there. So we call this a glycosidic linkage when we're feeling good. But for today's purposes, Amarachi wanted me to be ambitious with the catabolic. She told me to use a peptide and break it down. So I decided to try to be just as ambitious with the anabolic, and I built up a sugar. Would this probably take or release energy? The expectation is that this is going to take energy, that this is a non-spontaneous process. Lovely. Amarachi?
The semblance of glucose is that.
That's an alpha. I think there are probably some more obvious examples of anabolism and catabolism if you're not ready to start throwing down molecular formulas. I think we can go back in time and think about some other breakdowns and build-ups that you're familiar with. And so in math class today, someone, who was screaming it? Probably Anahita, was saying that she could take 6 CO2s and 6 waters and put them together to make glucose and 6 oxygens. That process you guys probably recognize the framework for photosynthesis. For photosynthesis in that other class, you guys know a lot, right? The light reaction, the dark reaction, citric acid cycles. This is all Margaret and I know. This is the whole process of photosynthesis as far as we are concerned. We're just gonna throw in one more decoration. We're gonna say it requires sunlight. Again, like we're simple. What is the Reciprocal, complementary, opposite. It's gonna be respiration, and so I'm just gonna write this reaction backwards and talk about how you can burn glucose in your brain. It's going like fire right now to make all them neurons fire. I am interested in a guest lecture about neurons and the action potential and how that relates to chapter 9, if anyone's feeling up to it. What? No, 9 is redox reactions. I want to know how the difference in concentration of sodium and potassium gives me a potential, like a voltage, and it makes stuff go. This is technically a combustion reaction. This is technically an oxidation reaction. Mohab knows that bleach and dye is an oxidation reduction reaction. I'm working on yours right now. Redox. All of today, redox.
Is that why we say we burn calories?
Yes, that is exactly why we say we burn calories. So the way that we figure out the caloric value of food is by putting it into a little, we call it a bomb. It's a stainless steel container, so its volume is constant. We put a little nichrome wire, which is a wire with a lot of resistance in it, and attach it to 2 electrodes. We fill it with about 15 atmospheres of oxygen. We put the food inside, we seal that baby up. We apply a battery to the other side that makes current flow through the nichrome wire. The nichrome wire gets real hot. It sparks, the oxygen burns, the food burns, we see how much heat is given off. That is how we know how much food is in your food. Yes. Like that's how the original measurements were done.
So does that mean that
So I don't know if we still do that for like every potato chip. At this point, I don't know if we don't break it down into its components. So you know, how many calories are in a gram of carbohydrate? 4. And in a gram of protein?
1.
And in a gram of fat? I've heard of the beer belly. I had a friend in college who decided to give up beer and go for straight vodka because he wanted to lose weight. No, why not? Because alcohol also has calories. Alcohol has about 7 calories per gram. Where's that in your little like litany of thing you memorized? So like other foods have caloric values, and different things have different caloric values. Like you might be better or worse at processing lactose. I'm guessing if you're lactose intolerant, that you know you may not be giving those 4 calories per gram of lactose if you were just like flushing it from your system into the toilet, right? Like they're weird averages. So I think the fact that things exactly match on packaged food to our understanding means that we now like just test for the amount of protein, and we don't like see if it's a good protein or a bad protein. Do you take protein? Like shakes? I feel like for a long time there was like a whey is better than this is better than that, like a ordering. Like what does that mean? Like why is egg protein the perfect protein?
I have a friend who makes their shakes with Oreo, protein powder, orange juice, spinach, eggs, and it's the most disgusting. It's not food. It's the most disgusting thing I've ever heard in my life.
It's nasty. It's disgusting.
He's like cream protein powder
And orange juice.
and spinach and eggs.
So I was surprised that Dunkin' Donuts makes protein powder now. What? Dunkin' Donuts makes protein powder. Like, yeah, that's the whole sentence. I don't remember why I was at Academy, but I was looking for some like lacrosse strings or something. They put the lacrosse stuff in the corner in the deep recesses of the store by the Dunkin' Donuts protein powder. Okay, you guys know this already, so I read it to you quickly. Anabolic reactions increase the complexity and order of biochemical reactions. The entropy of the system, therefore, must go down. I mean, look at it, going down. I'm tethering these two things together. They have a whole lot less agency if they've got to hold hands. It's like a three-legged race. Things that go from a less ordered state to a more ordered state imply that delta S is going to be negative, and we know that we have to provide the energy to make this happen. You are in an immensely ordered state. Remember that ATP synthase I talked about where I had 26 or so proteins that folded and then self-assembled into your cell membrane multiple times? That is why you guys laze heat. Like you are just sitting here giving off heat, trying to make the second law of thermodynamics not fail. If you're gonna make yourself super ordered, you gotta make a whole lot of disorder. That is the heat that you are exhausting to the surroundings.
But why is delta G greater than 0?
Because this reaction we think would be non-spontaneous. We think that we would have to provide energy for the building up of things. Like photosynthesis is a anabolic reaction. Generally speaking, we believe that these are gonna be energy requiring. So if you wanna get this into delta S, we can say delta G is equal to delta H minus T delta S. I'm trying to convince you that delta S is negative so that this whole term is positive, sort of supporting this. It's not spontaneous.
Delta S is like the
Delta S is the entropy, the amount of disorder. So we are reducing the disorder.
Okay, so
The
it's
final
not-
disorder is less than the initial, so delta S would be negative.
So what were you saying earlier about like it being counterintuitive to what we normally know as like when you
So
build
if
on-
I want to play chemist, which you know sometimes I like to play, my understanding is that breaking bonds costs energy and making bonds releases energy.
Yes, in chemistry.
Yes, like I feel that strongly, and so this is a bit counterintuitive to me that the process of making something would take energy. Right? That is opposite of how we think about bond breaking and forming. And it's because this is happening in an aqueous environment that it works slightly differently than you might expect. So,
This like catabolic like breakdown reactions happening with spontaneous all the time. Isn't that why people like die with natural causes? Because over time they're just like breaking down and breaking.
seems very reasonable. A little dark. So if you're asking yourself, how do you provide this energy to do things like this, to make yourself more complex? The answer is that you have to couple it with other reactions. So just like to do electrolysis, which was non-spontaneous, I had to put a big battery on the other side of the cell to force the electrons to do the unnatural. I've got to feed you like every day. I got to put 2,000 calories into you every single day to couple that with all these things that are non-spontaneous. Audrey would like me to go slightly faster. Okay. Oh, that one went all at once. Okay, let's talk about the elements that are in biochemistry. This will go fast. What's the most common element? Good job. What's its electron configuration?
1s2
What does it look like in terms of a orbital box diagram? Is this paramagnetic or diamagnetic? They're not all diametrically opposed from each other. It's going to be attracted to a magnet. How many bonds does carbon typically make?
4.
This thing only appears like it can make 2 bonds. How do I allow it? How do I give it the power to make 4 bonds? That's right. The first step of hybridization was promotion. And then we started mixing these together to make whatever it was we needed. That allowed us to make sigma bonds and pi bonds. Is a sigma bond made between hybrid orbitals or p orbitals? Sigma bonds are made between hybrid orbitals. So let me remind you what I'm talking about. I'm looking at this carbon right here. There are 3 things around it. With 3 things around you, you're going to be sp2 hybridized. sp2 means that I'm going to take an s and 2 p's and mix them together to make 3 degenerate orbitals. and leave one p unhybridized. The 4 electrons are gonna occupy these electrons, the orbitals like that. And I'm able to make 3 sigma bonds. That's the head-to-head overlap of the hybrid orbital and whatever it's bonding to. And 1 pi bond, that's the side-to-side overlap of unhybridized p orbitals. Oh, that's good. Give me like an affirmative. You're not talking things I've never heard of.
Which one's the double bond?
Pi, the side-to-side overlap of p's. So what I'm picturing is that I have a carbon here and a carbon here, and they're both going to use hybrid orbitals. And then I have a p orbital. Oh, I need the oxygen, sorry. I have a p orbital on this carbon, and I have a p orbital on that oxygen, and they can make the pi bond, the second bond, the side-to-side overlap of unhybridized p orbital. This was kind of a good job. I apologize. Oh no, I have these hard mock exams that are coming up in like 3.5 weeks or something. I'm getting all of this. What does it look like if we excite something?
From one energy level to the
So this would be an excited state, honestly. We took something from a lower level up to a higher level. So hybridization is the mixing of orbitals. So hybridization, we said, had to happen in 2 steps. The first one was the promotion in order to be able to make 4 bonds, and the second one was the mixing, which is really what the hybridization is.
So you took one of the electrons with 2s and 2 and 2p, and then what was the hybridization?
So I took the S and 2 of the P's and mixed them together to make 3 sp2 orbitals that pointed along the directions of a trigonal plane. Because if I look at this carbon right here, I can tell you its shape is trigonal planar. It's got 3 things around it. And then I'm saying that there's a p orbital. There's a p orbital here. Stop laughing at me. And a p orbital here, and that's what's making that double bond. So carbon is special because it's really good at making 4 bonds. It's really good at bonding to itself. It makes lots of covalent bonds. It makes lots of really big structures. What are some other elements that are common here?
hydrogen.
Like it? So someone went to the Chomp School of what's in biology. Really judgy. Generally speaking, we make fairly stable molecules, but it is possible, because the bonds aren't so strong, for us to change things around. So it's the balance between things being stable and things being reactive that makes all of this work. It's like a conundrum. It's like water. Like water is perfect for life. If water worked differently, life would be different. This is another one of those balances. The carbon-carbon bond is just strong enough to be stable and just weak enough for me to mess with it. So sulfur isn't very good at bonding to itself, is the issue. So when sulfur bonds to itself, it tends to make these little things that look grossly like stop signs. So it makes like a little ring. It doesn't typically make a big structure. And it's most stable. Sulfur also can be tricked into bonding just to 2 things, because it has those long pairs. It has to really want it to bond to something. Okay, so chomps. That's what that says in one of the world's worst photocopies. Math class, they're like, oh, your photocopies are so beautiful. I'm like, yes, judgy people. Mine are extra ugly today. So I wanted to think about how these 4, 5, 6 elements related to the different groups that we're going to talk about together. And so I'm going to start on the right-hand side with sugars. Sugars are going to be composed of just carbon, hydrogen, and oxygen. And we're going to build sugars up to make a class of compounds known as polysaccharides. And you've heard of starch, which will come in 2 flavors, and you've heard of fiber. So on the top, I have like the monomer unit, and at the bottom, I'm trying to make you the biopolymer. Carbon, hydrogen, and oxygen are also the ingredients over here in the fatty acids. We haven't drawn one of those on the board yet. A fatty acid is something that looks grossly like C17H35 Q. They got really long chains of carbon. I drew you a saturated fat where every carbon had only single bonds completely surrounded by as many hydrogens as I could shove into there, and then I put the acid on the end. That's stearic acid. It's a pretty common one. What makes it a fatty acid? Like, I understand the acid part, I drew that Q. I'm gonna make, okay, we can do that.
Is it like how it's like unsaturated or polysaturated?
So those are all true. That's all gonna refer to how we do this. But my answer is gonna be super stupid for you guys. It's gonna be, because this is hydrophobic. We call them fatty acids because this long tail is a hydrocarbon chain. It's hydrophobic. We can take fatty acids. They don't actually build into a polymer the way the other things on this chart build. Fatty acids will build into my life for a world where they buy markers every now and then, you know? Into a triglyceride, you guys might call it. You guys are gonna tell me if I'm doing anabolism or catabolism. I'm gonna take 3 units of stearic acid. Again, that's gonna be C17H35Q. And I'm gonna take 1 unit of what I call propane 1,2,3 propane triol. What do you call it, Audrey? What do you call 1,2,3 propane triol?
Oh, not bacteria.
Huh? No, I thought you had it. Well, I'm making my lipid. These things come together and the Q loses an H. The alcohol loses an OH. That makes a water. And it's going to bind these things to those things with what kind of a bond? Okay, it is a condensation reaction. Anyone who says ester gets a gold star. So you guys already told me what I called this compound, this class of compounds. If you were to eat a steak, I do believe you would be enjoying this particular juicy fat that vegetarians among us don't get a whole lot of. We like the unsaturated fats, the liquid fats, they're better. What do I call this? It's a triglyceride. What do I have tri of? Tri-fatty acids. So what do you think this is? Glycerol. So if Sophia were to take fat, like beef fat, like tallow is what we would call it at that point to make it sound polite, and make soap out of it, what would she leave behind? Yes, you make soap out of fat. Isn't that crazy? You take this and you mix it with lye. And when you mix it with lye, you break all of these bonds and make those salts. And so if you wash your hair, you have sodium laurate sometimes in your shampoo. That's sodium and lauric acid. I have stearate here. I don't think we put sodium stearate in your soap. But you make glycerin, And you have to decide if you want the glycerol to be in your soap or not. Have you guys ever used Neutrogena yellow bar soap? So use Neutrogena. Yeah, I'll take that. No, it makes your skin squeaky. And the squeaky is the glycerol. They're the same thing. Also, you use it for suppositories, so there's a fun demo you need to do. If you teach chemistry, I don't do it anymore because it makes too much smoke and I'm a loser. But the only place you can find glycerol in the drugstore is like with the suppositories. Like, what is my life? Anywho, this is in the category of things known as lipids. Lipids are the most diverse category in some ways that we'll talk about. We'll talk about triglycerides, which again you guys call fats when you're not being biologists. We'll talk about two other lipids. Any guesses? We talk about three lipids. One of them is triglycerides, or fats and oils.
Monoglyceride, diglyceride.
Phospholipids, love me some bilayer. And the last one is the reason that this isn't really a good description of biopolymers, it's because it doesn't actually have the fatty acid structure in there, but it is hydrophobic. It does not dissolve in water, so we put it in the same class. It's also made of carbon, hydrogen, and oxygen. It's going to be things like cholesterol, things like testosterone, things like estrogen, things we classify as steroids.
But are they not, but they're not technically fatty acids?
Right, they have no fatty acid in them, but they are called lipids because they are non-water soluble. So that is how we got them into one category. Everything else is going to be like monomer, polymer. And this is going to be like stuff that don't dissolve in water. Biologists are all about categorizing something, and this is where they left this. If we are willing to include some new elements, we can make ourselves some amino acids. One of them really great guys who is trying to figure out something about genetics did an experiment where he labeled sulfur and he labeled phosphorus, trying to decide how viruses like put like junk into you. And so the trick here is that we have sulfur in proteins because of amino acid methionine and his friend who I can't think of, but we have phosphate backbones in DNA. And so by labeling those two elements, which are unique between them, he could figure out that the viruses put the nucleic junk into us. CHONP. Who was that guy? Not gonna get there. So that's Hershey and Chase?
I don't think it is.
Oh yeah, it's protein. Oh yeah. So we're like that. Saw the
Okay. Unfortunately, I've already taught the other class, so I can't look smart for them. So like, let's pretend that I do that. Maybe nucleic acids are left for HL because they actually combine two of these groups. You guys are familiar with the nitrogenous bases, A, C, G, U, and T. They are going to be like the smallest unit, sort of this, but we're going to put those nitrogenous bases on two other things. What are the other two components that turn a nitrogenous base into a nucleoside and a nucleotide? Because y'all hate me. And so you'll see an arrow coming over from sugar. We're going to add a ribose sugar to turn this into a nucleotide, and then we're going to add that phosphate backbone to turn this into a nucleic acid. So the structure of those is definitely the hardest to convey. There's a lot of drawing there. You can see that I've trained myself to draw sugar. Do you feel like this is someone who has practiced drawing sugars? Like, I hope you feel that. Like, I draw a lot of sugars, and you guys are going to practice that. With the nucleic acids, I don't have that much practice. I have to think about which things, point where. But when you think about how is DNA different than RNA, one of the things on your list must be that it's deoxyribose. It's actually 2-deoxyribose. Where is carbon number 2 in a ribose sugar? And what does it mean to deoxy it? That'll be our life. They took an OH and replaced it with an H on carbon 2 in a ribose sugar, which is a pentose sugar. And so, like, how do you count? Where does the nitrogenous base add, and where does the phosphate add? Like, it's just... We're interested in the structure of these molecules. They hate everything. Of the 118 or so elements that we have identified, I think there are about 27 that have been found in the human body. Chomps are kind of the winners, but you guys are familiar with sodium and potassium channels. You're probably interested in how calcium interacts in muscles. You might know that there's some cobalt in cobalamin, which must be somewhere. There's some iron in hemoglobin, which must be somewhere. So, like, yeah, there are elements in you. Iodine, thyroid. How do we know this? We know this because there was a nuclear disaster in Fukushima, and all of the people in Fukushima started buying potassium iodide so that they could fill their thyroid, which is where I believe you store iodine, with non-radioactive iodine. A common source of iodine is seawater. They thought that the iodine in the water was going to give them cancer. So they decided to, like, saturate themselves with clean iodine so they wouldn't absorb any of the radioactive one. Good story. Oh, you already did that, thank God. Most common types of reactions we're going to have are condensation and hydrolysis. We drew one of each of these already, but the third type is going to be redox reactions, so we're going to talk about that in a second. Water is an important part of all of this. We already did that. We made maltose. You're going to make sucrose on your homework. That's the problem I told you was unfair. It's unfair because it doesn't tell you how to make sucrose, so if you want some homework help, if you want to actually draw the right structure of sucrose, you need a beta fructose, and they just don't tell you that. So I looked it up for you because it didn't make no sense. And if you don't know how to do that when I see you next time, we'll draw it on the board together.
Wait, is the anabolic reaction remind you polycondensation is
I didn't do a polycondensation because I didn't make a starch. I just did what condensation? But turning that into amylose would be the polycondensation. This is an interesting statement, so I'm going to make you call attention to it. Unlike traditional organic reactions where we're pretty happy if we get a 20% yield, biochemical reactions happen both very fast and with extremely high yields, and that's because you have enzymes that are so well suited to do what you're asking of them. It's amazing. If we can make enzymes for all of the things we're trying to do in a laboratory environment, we would be significantly more successful at drug design, for example. We're going to do this. Define oxidation and reduction in all ways possible.
loss of electrons, reduction of oxygen, loss of hydrogen, loss of hydrogen.
To me, 1 and 4 are the same. So let's pick on Sophia. Sophia is going to undergo a metabolic chain of reactions. That metabolic chain of reactions will take place in approximately 4 years. She is going to take some ethanol, and her body is going to convert it in 2 steps. First to ethanol.
I'm actually allergic to alcohol.
That's why I chose you, sweetheart.
Oh, yeah.
This is when we look for the phenotypically Asian kid in the room. What? It's a thing. It's not.
Oh, I know what you're talking about, yeah. No, it's not.
Okay. Like,
It was just funny.
yes. So there are actually two enzymes that take place in the processing of alcohol in your body. Your body starts with alcohol and ends with carboxylic acid, vinegar. It is this second step that many Asian people do not express the enzyme for. And so they get a high concentration of ethanol in their bloodstream, and that makes them flush. It is a reaction to poisonous ethanol. That's what makes you pink and hot. It's not really great for you.
Is it like a genetic thing, like evolutionary stuff, or it's just like some people have this happen? Because I know it is a thing like Asian flush, but is it like genetic or just like?
It's genetic.
My understanding is that it's genetic, that they just don't express this particular protein.
It comes with higher rates of cancer.
What? A lot of, like, yes, quite a lot of people. Fun example, right? How do we know this is oxidation reduction?
Because one of the things is losing hydrogen.
Here we're losing hydrogen, here we're gaining oxygen. So these meet the definitions, but Audrey is a perfectionist and she wants me to make sure with oxidation state. So she's gonna tell me to do 2x, because I don't know carbon, plus 6 times 1 plus 1 times minus 2 is equal to 0. And today I'm not gonna make a math error because it's feeling like a rock star day. I got an oxidation state of -2 for the carbon over there. Over here, I'm gonna take 2x plus 4 hydrogens plus 1 oxygen equals 0. One more time, my math skills on point. The oxidation number is going up. We are losing electrons. How many total electrons are lost in this reaction?
No electrons.
The answer is either 0 or 1, so keep guessing. 2, why is it 2?
Oh, because
Because what?
Because of that too.
No. Oh yeah, okay, I'll give it to Mohab. It's because of that 2x. It's because there are 2 carbons going from -2 to -1. So with 2 carbons making this change, he's suggesting I put in 2 electrons, and I finish balancing this with 2 protons. This one works the same, and it doesn't seem fun right now. Does it seem fun to you? Yes, dear. This time I have to balance with water, and then I can balance with protons. And so these are both oxidation reactions. Many of the reactions that take place in your body are such. You guys know some other ones. So I was never good at all the little helper molecules and all those little cycles you learn about. But like, I am familiar with NAD plus and FAD. And I don't know a whole lot about that. N stands for nicotinamide adenosine, and then it just keeps going on. I don't know, and I'm sorry, and I don't care. But what do they turn into? Correct? Okay. Let's think about that. So this is two examples of reduction reactions. You feel me? We are taking those electrons, but we talk about this in terms of maybe electron transport a little bit. And we talk about how different things hand electrons off to each other. So very high energy electrons and something that perhaps absorbs some light can take those high energy electrons and hand them off in a series of metabolic steps through an infinite number of metabolites to do the business of the cell. So the point of this is not that we need to know a whole bunch of reactions. The point of this is that redox is really a big deal if you want to do biology with purpose. So we can use different metabolites to transfer and store energy. And then we can move that energy around by giving those electrons to a new guy. And we balance all of these equations in aqueous acidic environment, the same way we did in chapter 9. So when Amarachi is sitting on that test being like, I don't know this metabolic pathway, I don't know what this weird molecule is, everything has freaking acronyms, I don't know what the molecule is, she just reminds herself, I use the same tricks I learned in chapter 9. Something I have not done a good job emphasizing with you is that the option is used to reinforce the core. They are looking for ways to apply this to oxidation reduction chemistry. Yo, can I make you balance a redox reaction the way you did in topic 9? Can I make you describe kinetics the way you did in topic 6? We're always going to be making those those backwards connections. So there's the one we talked about. We did that. We're not doing that. Don't care. We have written the reactions for photosynthesis and respiration. Respiration, one more time, does not mean breathing. The world is a crazy place. Some of you are like really good at knowing how many ATPs you might get out of this stuff. Do you not talk about that? Okay, keep all of that fun fact knowledge for your private biology consumption. At this moment in time, we're going to admit to each other that this process of respiration can be done in 2 ways. We refer to those 2 ways as aerobic and anaerobic. And here means without, just like it should, not anabolic, like it should not. What is it with and without, friends? That's right. So here I have oxygen. Here I don't have oxygen. Which one releases more energy? This one makes CO2. What are some fun products I can get from the anaerobic respiration of, let's say, yeast? Ethanol and lactic acid. How would I believe that animals can make lactic acid if they anaerobically?
Run your muscles too hard, and then you no longer have enough oxygen, and then it makes lactic acid, and then it hurts.
Rock on. Okay, so like I don't have details about this. Do you feel that? Like I know you guys have details about this that you learned in your biology honors class, because at some point I knew those details, but I don't know them anymore. Anabolic, catabolic? Anabolic, catabolic? How are these 2 reactions related to each other? Does that explain how carbon dioxide and oxygen cycle through our environment? Good. There's a question on the homework that says, like, write me a sentence. Write me a sentence. No. How much time do we have left? It's been an hour and 10 minutes since I've been doing this. It's 11:10.
Yeah, this is the last slide though.
Okay, let's try this for a second. So chlorophyll is going to be an example of a biological pigment. That's going to be B9. Can you talk about some other pigments? I know I listed them at the beginning. I'm curious what you got. Melanin. Carotene. Did you say hemoglobin? Thought I heard it, but yeah. Okay, so there's lots of them. So we'll talk about those. But one of the biggies is chlorophyll. What colors does chlorophyll absorb?
Everything else but green.
Okay. And that light energy is then gonna be used as a driver for anabolic reactions, that is the building up. What are we gonna build up? What else do plants make? They do make oxygen, what? Oh, yes. What do plants make themselves out of? Cellulose. What do you think cellulose is? A whole bunch of sugar is brought together. A whole bunch of starch is brought together in a beta one form like. What's the opposite of photosynthesis again? So what happens when you turn the lights off? The plants just respond. So that's the point of this. I don't know. Like I said, I didn't have much to say, that's why I skipped it, but then you said I had 10 more minutes to, I guess I don't need to. So it's the same thing. So apparently we always use a cow.
Cow farts are destroying the world.
It has nothing to do with cow farts.
The methane. Really lasts an
Always facing that way.
Okay, well, I'm glad you all know this picture. It's not one that I know very well. It doesn't really bother me too much. Are you guys watching The Last of Us?
I've heard of it.
Oh,
Once I find someone's HBO account to steal it, yes.
I hear it's like real
The adaptation of that game.
Yeah. They made it to a show.
Have you played the game?
I haven't played the game, but I've like seen
If I was in a zombie apocalypse, I think I'd just kill myself.
That's a good idea.
I mean,
Like, I would do the same.
I'm just not good about it.
What's the point?
Save others? Like, is this altruism?
No.
No, it's like that.
Or you just don't want to deal with it? Like, I just can't even.
Yeah, I just can't.
'Cause-
The Last of Us?
exactly.
It's on
What would you
HBO.
do if you somehow kill all the zombies?
Take over they take over people's minds, and there's one girl who's immune to the cordyceps, and so this dude
And how
has
are
to
you
take
gonna
her
do
to this
this
lab
if you
so
have
that these
zombies
scientists can
that
cut his
have
brain open so they can take some stuff to make vaccines for the fungi. But then when he gets there, he realizes that he can't just give this girl to these people who don't know what they're doing and also don't have a good plan. And he substitute her in for his daughter who died when the outbreak started.
That was very sad.
Yeah, it's very sad. And then the second one is even sadder. I tried to vote for them, and they're
No.
video games, but they're like story-driven games.
Oh, she's described the first episode at the beginning. It started as a video game and it's been adapted into a show and it's supposed to be the thing, but apparently now Happy Valley is even more thing-ish. It's a British show about like a police officer who's trying to avenge. No, I don't. I've never heard of it. I watch one show at a time and like my show's The Last of Us, so you know, an hour a week I feel like I can devote to TV.
I've heard that the first episode is very, very true to my life.
Yes, like you described the first episode like you had seen it.
I've seen the game. Megala said it was like frame by frame recreation of the cutscenes, and I was like, oh, thank God. Because they ruined too many games and shows for me.
Video game.
But it's cool because it's based on like the actual
Right.
stories in real life that takes over like ants' brains to go spread its spores.
Yeah.
And so like it's like that, but like scaled up to humans. It's really cool.
Well, you know, if you have free time, you have a stoichiometry problem to solve. If you don't have free time, I'm not going to blame you. You can also start your homework. How do you like homework?
I gave a 2 degree lead on the CO2 graph. The whole like 5, I like literally I gave up to 57. Someone said 58, and I said 9. And it was like
Did you give partial credit? Like, what did I give? Almost no partial credit.
I did 0.5 marks or like 1 mark for the first mark. I did that. I have a very like I use my brain where it's like method mark and answer mark. So it's like one method mark for putting it into a formula and putting that answer. And you go in
Yeah, I just
second
like, I'm
mark.
just now going to have to make the two the same, right?
I told him to.
I saw it everywhere.
I don't know, where I saw was not a whole lot.
Nickname, and then the number of kills.
Oh, it's Margaret.
And then if I was going to be 19, nickname was like season 4, like,
It
that's
worked
the
last
thing.
year
Really,
as well.
like, for people who like, I don't know this game. I don't regret reading the manga. But
I
literally
was
ruined
paying
my life.
attention.
It ruined my life because season 1
Don't-
and 2 is
I don't believe that there are a lot of questions about this use. I believe that there is some vocabulary and some like setting ourselves in context, but I don't think we want to say B2 and B7
I only say too much.
questions.
It's okay.
What I suggested I was gonna do is remove one question from a paper 2 and replace it with a paper 3 biochemistry. Like,
Really like my top, like one of my favorite. But like large stories, so high to reach, being emotional.
it should have been, I like that.
Okay, I gave you the.
I think that's what I sent to you.
It's really nice because it should turn the back with on.
Does it say 2 5 degrees?
No, it's 1 5
He lost his heart.
Is what I
He
sent
tells
you?
him that she loves
No,
him
the
so
key
bad.
that I got the one that had the
Yeah,
key.
so
Oh, I thought they were, okay.
I watched it.
So, yeah, so I answered that question.
Really, I